So in this lesson, we're going to look at a couple examples of applying exponential functions to real-life situations. So our objective is simply that. How can we solve growth and decay problems using what we know about exponential functions? So the first example we're going to look at is something that's very timely, and that is, can we model the growth of the COVID-19 virus using exponential functions? And when a virus first begins to spread through a population, it typically grows exponentially. So we can use our standard form of exponential function to determine those growth rates and perhaps predict its spread, which has been a big challenge over this past year. So we start with our form y equals a times b to the x. And y in this case would represent the number of people that have contacted the virus. A is how many people did we start with? And way back in the early days, right, we had our patient 0, the first person in a given area that was detected with the virus. So for the simplifying what we're doing here, we're going to assume that growth rate, initial value is 1. The growth rate is what we're going to solve for. And then X is our time period. In this case, it'll be number of days since the first case. So let's look at some examples. This was data from early on in the epidemic and comparing growth rates in different countries. We'll look at 3 that were particularly hard hit, right? Italy, Spain, and of course, the United States in the early days. So let's pull these numbers off the graph. Italy had almost 60,000 cases after 29 days. The United States had about 33,000 cases after 22 days, and Spain had about 28,000 cases after 22 days. Okay. So let's first take Italy and see if we can plug it into our equation here, right? So we have our total number of cases equals 1. We're going to assume it started with 1 person, times b, the growth rate we're trying to solve, raised to the 29th power. Now, how are we going to solve this? Well, the 1 we can get rid of. And to solve for the growth rate, right, since we're raising it to the 29th power, we can get just the growth rate b by itself by raising that by the reciprocal of that power. So notice we're going to raise it to 1 over the 29th. And that will allow us to eliminate the exponent on the right-hand side. So we need to do the same on the left. So we grab our calculator and take 59,138 and raise it to the 1 over 29th power. Probably want to put parentheses around the 1 divided by 29 when you use that as your exponent. So we do that and we get a growth rate of about 1.46. So one way to think about it is each individual person in the next week would pass the virus on to 1.46 more people, or a little more, almost 1.5 people. And this is a key metric that health officials use to determine the rate at which it's spreading. If it's below 1, then it's going to shrink, right? If it's greater than 1, then we have a spread of the virus. So each day, the number of people infected grows by 46% or 0.46. Now, we can ask another question now that we have the growth rate, and that is, how many days then would it have taken for 25% of Italy's population to have the virus? Now, this would assume, right, that we don't put measures in place to slow the growth of it, that it continues to grow at this rate. And as we've seen over the past year, right, we put measures in place, we have lockdowns, we wear masks, and it can slow this rate. And we kind of have waves that have occurred also over the past year. But let's assume that we continue growing at this rate. Italy has a population of about 60 million people. So if we take 1/4 of that, we'd have 15 million. And we want to figure out how many days it would take for it to spread at this rate. So we're going to solve our exponential equation by taking common log of both sides. And we can move x to the front using power property. And now the rest is calculator work, right? Take the log of 15 million, divide that by common log of 1.46, and we get about 43 days. So growing at this high rate, it would only take about a month and a half for a quarter of the country's population to have the virus. So let's do the same thing for the US. We're going to raise it by 1/22, both sides, and we get a growth rate of 1.61, actually higher than what Italy was. So let's do the same thing. How long would it take at this higher growth rate for the US to reach 25% of its population? So we're going to, again, set it up as an exponential equation, solve it by taking log of both sides, and we see it would take less time, about 38 days. And it makes sense, right? The higher the growth rate, the fewer number of days to reach a certain portion of the population. And I'll let you now do this for Spain. And we'll assume 47 million people live in Spain. Okay, so if you work that out, you should have found a growth rate somewhere in between what the US and Italy experienced early on, and the same thing with the number of days to reach 25%. All right, let's look at an example now of exponential decay. And this comes from chemistry, or kind of physics, the half-life of isotopes. So if you're taking chemistry from Mr. Deller, you'll probably have studied these, or will at some point in the year. And the isotope is a form of an element that has a different number of neutrons and protons, right? A normal element has equal number of neutrons and protons, but isotopes are typically missing a proton or have extra neutrons. So let's look at an example. Carbon has an atomic number of 6, which means it has 6 protons and 6 neutrons. Carbon-14 is an isotope that has 2 extra neutrons, so 6 protons and 8 neutrons. Now, isotopes decay. They're not stable. They don't stay in this state forever. They'll decay into the normal carbon atom with equal numbers of protons and neutrons. But each isotope has a unique time it takes to decay. We call this the half-life. It's the amount of time it takes for an isotope to decay or disintegrate to 1/2 of its original amount. So for example, the half-life of carbon-14 is 5,730 years, right? So this process happens very slowly. And carbon-14 is a common isotope that archaeologists use to try and date old material that they might find when they dig things up, or looking at fossils and trying to figure out how old they are, because they can look at how much the carbon-14 isotope has decayed in that sample. All right, so let's look at an example where we can use our model of exponential growth, or in this case, decay, to make some predictions. So let's say we started with 244 grams of carbon-14. So that will be our A value. How much would remain after 100,000 years? And remember, carbon-14 has a half-life of 5,730. Now, the half-life, by definition, means that our decay factor will be 0.5, or 1/2. Okay? But what are we going to put in for X? Well, that's where we are going to put in a ratio of the time period that we're analyzing divided by the half-life. So you'll see 100,000 divided by 5,730. Okay, so we really have all of the values here that we can plug in and determine how much will be left of the original 244 grams after 100,000 years. So let's go ahead and do that. We plug all these numbers in, and then it really becomes an exercise with our calculator. So first thing to do is 10,000 divided by 5,730, and then raise 0.5 to that power. Multiply that by our starting value, 244, and we see that after 10,000 years, we would have about 72 grams of material left. So if we're going from 244 to 72 grams. Now we can ask another question: how long will it take for our isotope to decay to 10% of its original amount? Okay, so now we're going to solve for that time factor. So how would we set that up? Let's look at it here. Right, we'd still put in 1 as our A value, because we're going to just normalize this. It doesn't tell us how much we had in terms of grams. So we'll just say we had 100% or 1 to start with, and we want to have it get down to 10% or 0.1. So that's why we put in 0.1 here for Y. Growth factor or decay factor is still 0.5. And then we're going to raise that. And notice we don't know how many years. That becomes our variable X that we're going to solve for, but still divided by the half-life, 5,730. So we don't have to worry about the 1. We're going to solve it again by taking the common log of both sides. And we're going to move our exponent, X divided by 5,730, to the front. Now, this could be a little bit messier to solve, but we can do this, right? Let's take the ratio of the logs, log of 0.1 divided by log of 0.5, and then we're going to multiply that, right, by 5,730 to get X by itself. And we get our final answer. So it would take about 19,000 years for us to get down to 10% of the original value of the carbon-14 isotope. All right, so that's it. We've seen some examples of exponential growth, looking at the spread of the coronavirus, and exponential decay, looking at how isotopes that occur naturally in nature decay over time based on their half-life.